Yeah, great.
So it's a matter of a great pleasure for us to get back Amir Ashuri, who's a past PhD student in our group, working with me and Professor Gianluca Palermo on compiler autotuning for machine learning. Currently, he's a postdoc student at the University of Toronto in Canada. So welcome back today for this seminar.
Thank you.
And thank you very much for accepting this invitation here.
Thanks for having me here. All right, buongiorno. So I'm very happy to be back here on the school that I had my master's and PhD. So today I'm going to be talking about the topic that I was mostly working on for my PhD dissertation here. So we recently had a survey from this topic, which is called compiler autotuning using machine learning. So, and the survey is just will get published in a month or so. So I try to sort of conform to that structure of the survey and adopted my presentation based on that. So Christina already presented all the background. So right now I'm a postdoc at University of Toronto. And so let's just go into the outline of the talk. So first I'm going to get started by the introduction of the problem and the concept of compiler optimization. Then I'm going to go forward with the characterization technique, different machine learning models, prediction types, and different ways that we can explore the optimization space, and finally the target domain. And the very last slide, I'm just going to talk about the influential papers that we had in the past 20 years. So this was the screenshot of the organization of the paper that we had in a survey. So for this talk, I'm trying to conform to that structure. So when I start, I'm going to start with the compiler optimization concept, characterization, machine learning, and so on. We had another concurrent version at arXiv. Since after you publish something, you don't have the access to revise it. So we plan to update that arXiv fork of the project quarterly. So if any paper came out and I wasn't, noticed, please let us know. I'll be happy to include it in the next version. All right. So let's just get started with the introduction. So just like after Moore's law, so another lesser known Probstein law came out. So it was a professor at University of Arizona, and he was thinking that starting from the compiler technologies and the compiler design from the late 50s. So if you just go forward and you extrapolate up to now, when you have some advances in compiler and you use the same version of the compiler and you compile the code with the highest level of optimization, and if you divide it and distribute it over the years, so you're going to have an advance of double the speed up, like 2x speed up every 18 years. So, and that got sort of famous as, by his own name, Probstein law. So, and the main focus of this law is no matter what the optimizations are, we are still far behind the architecture's technology. So this law has some pros and cons and some caveats as well. So although this intrinsically talks about lack of having optimization in the compilers, but on the other side, if you take a look at it from the other perspective, we need to have more autotuning in order to cope with the increase in the hardware technologies. And also at the same time, we have to adopt new machine learnings in order to solve that. And we have to leverage more accelerators, FPGAs, DSPs, on top of this. All right, so I'm just going to go quickly on this slide. So the compiler, module, you just input it with the source code, and it's going to output the binary code that the machine understands. And if you go back, you have 3 major layers: front end, middle end, and back end. So under each of these layers, you can have different optimizations. So you input your application, C++, Fortran, or whatever language you're interested, and you pass the front end and at middle end. So in some compiler frameworks, they call it IR, intermediate representation, you have some optimizations available, and at the end, at the back end, you generate the assembly code. So what the compiler Autotuning targets normally is taking use of the front end and middle end optimizations and start optimizing the code without the with the less knowledge of the compiler developer, so it can be easier to optimize the code from the outside. So as an example, we have loop unrolling, which is a well-known compiler optimization. Suppose on the left side you have a loop that is going to go for 100 times. So you can unroll the loop in a way that instead of looping for 100 times, you're going to loop for 20 times. So if you manage to have multiprocessor, or if you can accelerate it using other accelerators, you can have theoretically up to 5x. If you don't have any interdependencies as well, you can have theoretically up to 5x speed up. Another famous optimization is called loop tiling. So instead of going towards these two dimensions I and j, you can tile it, for instance, by 2 by 2, and you traverse the space in a block of 2 by 2 tile instead. So you're going to have more advantage if you want to use the locality of the cache. And so, theoretically, you can have less cache misses in this case. All right, so that was a general introduction of the compiler optimizations. So we know that we have a wide range of families of parallel architectures, both on the embedded domain and on the HPC domain. And so for each of them, different goals are intended to have. For instance, in embedded domain, we are interested in controlling the power and area. Area was mostly in the past. And also at the other end, for HPC applications, we are interested in having the highest possible performance to get. So because of these scenarios, there are some standard optimizations normally start with O, available in most of the written compilers. For instance, OS targets code size, OX, and X could be 1, 2, 3, and at some point, at some compilers, we have 4. So it's going to optimize your performance. And OFAST, it's going to add more approximations, so you're going to have less precisions, so it's going to go faster. So these are standard optimizations that are available in state-of-the-art compiler, but are we going to get sort of more customized way of generating our own optimizations vector and take advantage of the available front-end optimizations to optimize the code? So this is I generated this chunk of hexadecimal out of this code, and one of the definition of compilation could be be considered as translation. But if you want to be more correct, so compilation could be considered as translation plus optimization. So while you translate the code, you can optimize as well. And this will start the generating the problems that we have in Autotuning field because when you translate your code, you can optimize it using optimization number 1. But if you have other optimizations like optimization number 2, 3, 4, and 5, so each of them, when you optimize, you have different hexadecimal output, so different binary, thus different performance. And this will lead to a very large design space. And if you just play with the options, play with the phase ordering of those, and if you just repeat at some point some of those optimizations, you're going to have more and more version of the same code that at first sounded very easy to generate. So at the end, you're going to have billions and order of billions of parameters to have, and it's going to make it very difficult to choose which of them are yielding the best results. So in fact, you have billions of those combination of optimization to choose, and that's exactly what the compiler optimization and compiler autotuning field tends to answer. For instance, in the recent compiler frameworks like LVM, GCC, or Intel ICC, we have more than 100 and at some point 200. So, as I mentioned, this leads to a very enormous design space that you have that lead to generate two major problems that are so-called selecting the right set of compiler passes, or not only selecting those, but playing with the phases and have repetition of those compiler optimizations. All right, let's just have a quick definition of autotuning. So autotuning stands for automatic tuning, and it's going to address the automatic code generation, code optimization, while we are enabling different scenarios. So for instance, we are trying to maximize the performance and minimizing the cost. So it could be power, it could be area, it could be energy consumption. And the state-of-the-art autotuning for the past 20 years are leveraging machine learning techniques in order to come up with a solution. So that's a very broad and high-level view of a sample autotuning framework, a sample and classic supervised, machine learning framework. So starting on the left, upper left, you're going to train your model. So you are interested in training a predictive model that can predict some good compiler optimization for you. So if you want to train that model, you have to start with generating your design space, using your different benchmarks. So starting from optimizing the design space of experiment, if you are generating different versions of the same code, you use the compiler backend and you generate the binaries, and then you measure the output of those, and you can generate feature vectors out of each execution, and you train your model using any predictive model that you like. It can be deep learning with different layers, or it can be the old standard or conventional machine learning like linear regression, MLP, or random forest, or any other predictive models that you're interested in. And at the prediction time, when your test application, the application that you want to optimize comes, you are extracting the features so that you let the predictive model knows that I'm trying to optimize this application by having this type of features. So these features could be features taken from source code of that application, could be taken from the intermediate level of that application, and also could be fetched from the dynamic characterization of that application while you were running that application. And at the end, the predictive model will let you know that the outcome that could be the best compiler flags or the speed up of those would be. And then you can use that to optimize your application. All right, so let's just have a quick definition of the two problems that I've already mentioned, the selection problem and the phase ordering problem. So in general, when you have several options to choose in optimization theory, you're going to have an optimization space. Depends on the way you choose the optimizations. It's going to be in the order of NP or NP hard or NP complete. So on the case of the selection problem, suppose you have n optimizations, and each of those n optimizations have p available optimization levels. So in this case, you're going to have a exponential optimization space p to the order of n. So suppose you have 5 optimizations, and each of those 5 optimizations had 3 optimization levels. Actually, this should be p. So these 5 optimizations are loop unrolling, tiling, DC, loop fusion, and mem to register. So when you are having the selection problem, it means that you can select a subset of these optimizations, or select none of them or all of them, and also play with the number of optimization levels that each of them brings. So for instance, on this case, you are doing the loop unrolling with a factor of 3 or tiling 2 by 2. So these are the levels that a specific compiler optimization had. By having these 5 and 3 optimization levels, you have these examples as the variety of your optimization space. So by only having this small number of optimizations and very little optimization levels, you see that you have 72 different choices to make. And so just suppose if you go to LLVM board with having more than 100, 150 or 160 optimization levels, you're going to have billions and billions of combinations to choose, and each of them can lead to a different, version of the same code. And it's going to make it very hard to tune the application manually. All right, let's just define in the state of the art what the researchers were doing in order to tackle this problem. One of the famous techniques was iterative compilation. So as it sounds from its name, it's going to iteratively tries to recompile the same code using different combination of compiler optimizations and simply choose the best flag. It's very intuitive. It was introduced late 90s. It's like you have somebody tossing a coin for you, and by each toss of the coin you have a new vector of optimizations, and you're going to test that vector and capture the results. The advantage is, of course, when you just run forever, you generate more and more optimization vectors and you test them. In the long run, you have a very nice speed up graph for you to show, but sometimes it takes forever to reach that speed up graph. And also, since you don't have any machine intelligence to that framework, when a new application comes, you have to start from scratch. So you don't have any transfer of knowledge from what you've been doing for the past 6 months, so that you can transfer it and take use of it for the new application. So what we can do here, can we do better? The downside is, of course, as I mentioned, we don't have any knowledge transfer. So people have started to employ machine learning techniques, as I mentioned in the previous 2 slides, to train certain models and use them at prediction time to generate the best predicted output for us. All right, so that was mostly working for the selection problem in the late 90s and early 2000s. Also, there was another major problem in the compiler domain that was called phase ordering. So suppose you have that selection problem, but instead, not only you are interested in selecting certain compiler optimization, but also you are interested in finding the ideal ordering of those. So what if I can change optimization number A and B and use them in reverse order? So it might just obliterate the effect that compiler optimization B could have done on the program, or vice versa. Or what if I can have 2 optimization B in a sequence? Sometimes you need certain optimization that generate dead code elimination, and then other optimization levels that you need to have another dead code elimination after that. So you're going to have a repetition of DCE in this case. So what we can do here, definitely the optimization space would be much, much larger. And as you see here, using the same 5 optimization that I mentioned in the selection problem, and just bounding our optimization vector up to 5, so we have maximum 5 optimization in our vector, you see that we have many variety of the same optimization, compiler optimizations, and simply by having 5 and a boundary of 5, you have 4,000 different selections to have. So you see the phase ordering problem is a much, much larger problem with respect to the selection problem. As an example, suppose you have 20 optimizations. The selection space would be 10 to the raise of 7 almost. But on the phase ordering problem, even without the repetition case, you have 10 to the raise of 18. And it's simply impossible to generate and test all those using iterative compilation without the machine learning knowledge. All right, so when you have this huge space, people have been trying to downsample their optimizations. There has been so many other techniques, so I'm just gonna go through them in a very high level manner. So they've been using random clustering, manual clustering, or automatic clustering, and they've been using speed up predictions versus sequence prediction, and I'm going to describe it later in this talk. All right, so that was the concept of the compiler optimization and the 2 major problems. Let's go see what are the characterization techniques we have in the field that people have been using for the state-of-the-art problems. So let me just go back to the high-level graph that I mentioned. So here, one of the major components here is the feature extraction, and we have to do it, in order to understand the behavior of our application. So feature extraction, the output of that is going to, generate us some numbers, some vector of features. We call it feature vectors. That these feature vectors are representative of the characterization of the same application we have. So when we import that to our model, the model will understand that that specific application has this type of behavior. Is it cache intensive? Is it having so many dependencies between the variables? How many variables we have? What are the number of loops we have? Are they nested or not? So these are the type of features we can get by characterizing the applications, and this has its own classification in the field that I'm going to show you in the next slide. So in order to generate that, it's obvious that we have at least one pass or a number of passes over the application to collect its representative features. So these vector features will be used inside of the application in order to feed it to the machine learning model. But simply you have to conform with two simple conditions. Because we are using a machine learning model, it should be representative enough of the application. So when we train the model will be accurate enough. Another point in order to consider is different applications must not have the same features. Otherwise, the model will confuse and you don't have the optimal results as the output. So if you conform with these two conditions, you're going to have sort of a good enough representation of your application. Alright, so in the field we had 3 different characterization techniques. One of them is dynamic. When you run your code and when you generate your binary, when you run it on your actual architecture, you can characterize it dynamically while it's running. So one of the examples in the field, it was a tool called Milan that was a plugin for Intel pin tools. So it was macro, so the name was coming from the abbreviation macro architectural independent characterization of applications, and it was using pin in order to instrument your code while it's running dynamically. So, of course, the positive point of having a dynamic characterization technique is it's going to be fine-grained characterization because you have the actual output of running the application. You're going to see the actual cache misses. You're going to see the actual memory usage. You're going to see the actual number of parameters, and all so on and so forth. So it's going to be more fine-grained. Thus, you have higher accuracy. But as a negative point, some of them, except this actually, many of them could be architecture dependent. So when you change the architecture, you no longer are able to use your feature vectors in order to have cross-validation between different architectures. And of course, since you have to run your code every time, it's going to be slower to collect. So let's see what are characterization techniques we had. Another way, which was way older than the dynamic characterization, is called static analysis or source code characterization. One of the famous projects was MyPost, Gregory Fortin's EU project. So this type of characterization doesn't need the code to be run or executed. You just have a pass on the source code and statically analyzing the source code features. So the positive point of having this is, of course, it's faster to collect the features, and also it's independent from the architecture because you're not in a point to run it. You just look at the source code and you characterize the source code statically. So while this is good, on the negative point, it doesn't take into account the input data set. So if you change your data set, it's not going to change, so you're going to miss that accuracy if you're interested in playing with a different input size. Thus, it's going to be lowering accuracy. The third one that we we tested it in one of our recent works was sort of a hybrid type of characterization. So we employed these two and normalized it to generate a super feature vector, and we called it hybrid characterization. So it takes use of both of the cases, and at some point it's going to outperform both of them. So that's another way to characterize your application. So that was the example of the Mika, the first one that has a dynamic characterization. So it was giving us around 100 features on 6 categories. So these are the different 6 categories you can get from the Mika projects. So you have the instruction types, the PPM, number of registers, the strides, and also all the memory footprints information. All right, so let's go to the machine learning models now. Now that we know how to characterize the code, let's see what type of classifications of machine learning models we can use in order to train and use for our problems. So in general, if you want to classify the machine learning domain in a very broad and classical way, you have supervised learning, you have unsupervised learning, and you have reinforcement learning. So under each of those categories, you have many different sub-branches, and also letting alone the deep learning era that takes advantage of all these 3. You have a subversion / deep learning mode of that specific machine learning tool as well. So as an example, I was bringing some of the machine learning details of our recent paper, Cobain. So that specific paper was using Bayesian network. So I'm going to just describe what a Bayesian network do, and in this specific domain, how it did help us to generate optimal solution for our problem. So we had to first characterize the application and to see how we're going to maximize the performance. So that was a description of the problem. So for input, if you want to test your scenario, you have to sort of input the model, the characterization, which is called alpha here, under analysis, and the output would be the best sequence of optimization vectors, which we call it O bar, to use in order to maximize the performance of our application under analysis. So that was the description of the problem. All right. For this problem, we use the Bayesian network. So as an example, I put a sub tree of that Bayesian network. So as you see, it has 2 different layers. So on the first layer, you have the alphas, alpha 1 and alpha 2. So these are the characterization of my application. And I'm trying to correlate them to my optimizations and the optimization itself. So while the application characterizations are correlated with optimizations, I'm interested in understanding the behavior interdependencies between the optimization itself. So that's why you have another level after the characterization level as the optimization level. All right, so Bayesian network is a probabilistic graphical model expressed by graphs, and you're going to have a dirichlet acyclic graph, so we call it DAGs. So the DAGs here are based on the probability distribution. Thus, it's a statistical model. As an example, so when you have when you want to describe a very simple problem using Bayesian network, suppose you have 3 Boolean variables. Either the grass is wet or not, so 0 and 1. Either it's raining or not, or either you've used your sprinkler to wet the ground. So these are 3 Boolean variables. If you generate this correlation using your DAGs, for each of the states, you're going to have a different set of distribution and probabilities. So for instance, as the input, you have 20% chance of having rain and 80% of not having rain. And when you correlate the rain to Springer, you're going to have, when you have, so these are the input to our to our outcome. Suppose you have, when you use a sprinkler to wet the ground, the chance that you don't have rain was 40% only. So when you combine these two, the output of that Bayesian network using the probabilistic model would be, of course, when the grass is wet, definitely you either have rain or you had somebody to wet the grass using a sprinkler. Or on the other extreme side, if none of them has happened, definitely you don't have a wet grass. So as you see, this is very intuitive to describe your problems, and you have all those different layers in the middle of these two extreme ends. And we just adopt this model for our characterization and the optimization problems. Because simply there's no theoretical way or analytical way to fit a vector function O while we have the characterization alpha. Thus, we have to use a machine learning base such as Bayesian network to infer its probability distribution of the sequences and infer some knowledge and use it as sort of an approximation to generate the outcome. All right, so I mentioned that we use the classical supervised learning flow. We started by application characterization, and then we trained the model. So this phase is called model induction. And at the prediction time or inference time, we were using the trained model in order to, input them some evidence. In this case, the evidence was the application characterization, and the output was the best compiler flags to use. So again, another high level. So at training phase, we started by training our application. We characterize the application. We used PCA as dimension reduction, so we wanted to reduce our space, and we were training the application using our top-end solution because we were interested in the model to be trained only with good solution. So when we have a new application, it just predicts optimal solution for us for the target application. All right, if you remember this example, we adapted to our own problem, and this is a sample result out of that. So we were using 10 principal components. So you have PC1 to PC10, and we could correlate each of the component of the application at the first level to our optimization, compiler optimizations, and within compiler optimization itself. So you have two, as an example, I highlighted in blue and red two different major information that we can gain out of this specific Bayesian network dots. So for instance, on the red arrows, we see that both of our three optimizations were correlated to each other, and also they were correlated to that specific principal component of my application. On the blue arrows, you see that loop unrolling impacts my branch optimization as well, which is intuitive. So we could generate this for all our applications and data set in our training data. Thus, it would just bring good customized speed up for us for our training data. All right. Now that we know how we're going to characterize the application and sort of what type of machine learning model we are trying to use, let's see what the prediction type or prediction outcomes were mostly used in the compiler domain. So the compiler retuning domain in the past 20 years were interested in defining 4 different outcomes out of using their models. The first one, just like what we did in the Cobain, using our Bayesian network, is identifying the right set of compiler sequences. So the compiler sequences would be the outcome of our machine learning model. Another way that people used machine learning for compiler domain was to predict the speed up of a compiler sequence. So this means that instead of you run your specific sequence and see the speed up that it brings with respect to your baseline, the model will predict the speed up for you, so you don't have to run it. So this will be beneficial if you want to run like 10,000 times different combination of compiler sequences. So if you have a model that tells you this is the predicted outcome of this sequence, you can simply generate all your design space and input it to your machine learning model, and at each prediction time, you're going to have the predicted speed up of that, and it's going to be faster than your device or on your HPC domain to be run. So you're going to have you can just sort it by the prediction speed up, and in a matter of seconds, you have the optimal solution available for you. So that's good in this specific case. It has its own two classifications that I'm going to describe in the next slide. And so another way to, another outcome that people were interested in having was to cluster or downsample the optimization, because we have so many optimizations, they were interested in downsampling the compiler classes. And the fourth one, which was lesser known sort of in the field, was using machine learning to identifying the right set of application features to use based on each application. So these were, if you want to classify the work in a state of the art, these are the four different prediction outcomes that people intended to have. All right, let's just have a look at these two different way of doing speed up prediction. So we have intermediate speed up prediction and we have full sequence prediction. So this was we didn't have any literature before 2017, but lately, like 6 months ago, we had a new work that was accepted as ACM Taco. So we have one work on that subdomain as well. So if you go for intermediate speed up prediction, suppose you have applied optimization A called DCE on your application. So you are in the state optimized DCE. At this point, the intermediate speed up predictor tells you what to apply next. I'm not interested in your past history, but I'm just taking a look at your current status, and have another pass of application characterization at this state. And at this point, I'm going to tell you what to apply next. If you applied A, B, and C, you have to characterize another time and let me know that you are at this state. I'm going to let you know to apply maybe B another time. So this is called intermediate speed up prediction, because at each intermediate step, it's going to predict the next available, good optimization to apply. If you go for full sequence, it's going to let you know at one shot that this is your application. Just use this sequence of optimizations at one shot, and sort of it's going to be harder to build as a model, and I'm going to show why. All right, so this is a sample. Suppose this is your intermediate speed up prediction model, and you have a stop condition. The stop condition could be reaching certain speed up points like 1.5 or 2, or certain iterations. So you are interested in optimizing your code up to 10 iterations. So this could be the stop condition. Unless you haven't hit the stop condition, it's going to carry on predicting new optimizations for you. So your program comes. I deliberately make this one distinguish with respect to the others, because it could be another state than your baseline, which was shown in blue. So your application comes at the state X, and so these are the features of the programs you characterize, and you're interested in the next best optimization to apply at this specific state. It's going to query your model, and it will tell you at this point, for instance, use optimization A. So when you apply optimization A there, you're going to have a new round of feature selection, and I made sure that we have different type of characterization here, because by applying A, your features has changed. Another time you have another pass, and your optimization pass contains A as its previous state. You're going to query your model again, and it's going to let you know at this point apply B here. And this Since you haven't hit the stop condition, you're going to carry on. You have another round of characterizations. Your components of the program has changed, and the model again tells you at this point it's beneficial to use another B as a repetition of the optimization. And then finally, for the sake of the example, you hit the stop condition, and thus it's going to be A, B, and D, your final optimization passes in order to use for that specific application. All right. So what if you go to for a full sequence speed up prediction model? Your application comes, but at this point, instead of being in a state mode, you're always in a baseline. So you need one round of feature selection, feature characterization. You're going to query your full frequency speed up model, and at one shot, it's going to let you know for this application at baseline, use this vector of optimizations right away. All right, so this has its own pros and cons because definitely it's going to be more beneficial for you. You don't have to have at each state another round of characterization, but it's a little bit harder to make unit encoding in order to traverse the space, make sure that you have a fixed length variable, and so on and so forth. I'm not just gonna go into details because it's gonna make me run out of time. All right, let's just have a quick review of the latest work of us that was implementing this specific prediction model. We were trying to before applying the full sequence prediction, we were trying to cluster the available optimizations in order to downsample our optimizations. So in LLVM world, the -03 of LLVM has 158 optimization passes. Out of those, 60 of those passes are unique passes. So you see that even in real-world compilers, you have so many repetitions of the same passes. So we started by, generating, representing a graph-based representation out of our, an optimization 03, which on that specific case, we was the set of ops as a node, and E was the set of dependencies that we showed by edges. And we make this condition E of Vx, Vy equal to 1 only if we have a pair of optimizations that are consecutively appears in the optimization 03. So we were parsing optimization 03, all those 157 optimizations, and we were pinpointing all those consecutively appearing nodes inside that optimization path, and we were building up numbers for each of those pairs, each of those 60 pairs. So based on this, you can generate an optimization dependency graph. So these are all those 60 unique optimizations, and the wider the arrow you have, it showed that you had higher number of consecutively appearing together on that specific optimization path. So using this optimization dependency graph, we could see that what are the precedents and what are the predecessor and successors between each of the pairs we had, and we can see the correlation between each of those optimizations. So at this point, we can simply apply a clustering method to cluster our huge optimization space into a smaller space, while we are preserving what it meant to be preserved by compiler designers when they were iteratively coming up with 03, because at some point when they were constructing the compiler, they were seeing, okay, this set of optimizations makes sense to be paired together. So we try to preserve what it meant to be preserved, while we can cluster and downsize the optimization space. For that specific problem, we use a clustering method. We could use any other available clustering method like k-mean clustering or other available in the state of the art. So it was iteratively passing over this dependency graph and adding more clusters by using k nearest neighbor, and it was iteratively trying to add more while it hit the condition that it had, which was called path integral. I'm not going to describe the details because it's going to take time. So just conclude with this, that it was iteratively clustering using k-mean cluster unless it hit the condition of path integral of the graph. And the output was, instead of having 158, 157 in your path, you can have only 5 subsequences. And each of the subsequences have internal ordering fixed inside. So instead of playing with all those and generate a billion, different design space, you can play with only these 5 and generate only, 4,000. So these are externally can be changed, modified, but internally these, ordering are fixed. And this was a huge difference in order to generate your model, because this solid line was the exploration, the iterative exploration of our introduced, subsequences, and these 3 are the exploration of the same compiler optimizations while we were using a baseline such as O1, O2, and O3. So you see, because simply we didn't have any baseline, of course we start much lower, but at the very last, we outperformed the upper bound that O1, O2, and O3 could have brought us here. And this was the region of interest for us, because if you're able to reach this region of interest and outperform your O1, O2, and O3 by around 20%, when you pair this with a machine learning model, you can easily, in 2 or 3 steps, you can jump and come back to the region of interest, and always you have this 20%, 10% advantage when you predict new results. So in this example, for instance, it was beneficial for our work, when we use the clustering. All right. So that was different prediction types. Let's just conclude the talk with the remaining space exploration and target domain. So looking at the papers in the state of the art in the past 30 years, we see that we had 3 major techniques in order to traverse the optimization space. So the first one was sort of an older one. It was introduced by Cooper mostly. They would call it profile-guided optimization, so as an adaptive compilation. The second one was much older than adaptive compilation. It was mostly used in 70s and 80s. It was tend to bring the global optimization approach for our compilers. But nowadays, because we have so many variety of optimization to choose, there is no definite global outcome. Thus, this subfield was remained sort of static at this place. And recently, we have more and more papers pairing iterative calculation with machine learning, because you're iteratively approximating better and better solutions, and by traversing certain segment of the optimization space, you can